when our goal is to secure permits in a timely manner, and often we need them fast. Our ability to do so largely hinges on a comprehensive understanding of several critical components. This includes not only the underlying science and engineering principles of stormwater management, but also a firm grasp of the specific regulations, rules, and established practices that guide permit applications. By thoroughly understanding these elements, you can significantly streamline and accelerate the entire permitting process. Tools and specialized software, such as BMPFast, are also designed to assist in these efforts, helping you achieve that desired quick permit approval. In this section, we'll cover two key learning objectives. First, we'll explore how new rules, regulations, and evolving practices significantly affect stormwater management water quality permit applications. These guidelines are not static, they change quite a bit over the years, and keeping up with those changes is absolutely essential for any professional aiming to complete a job efficiently and correctly. Our second objective is to identify what resources and strategies can be used to assist in obtaining a permit in a timely manner, while also ensuring consistency with the very latest regulations and best practices. We'll be looking at what's in our stormwater toolbox. This toolbox is conceptually full of vital elements. It includes foundational ideas and concepts, current regulations, extensive reference libraries, effective treatment best management practices or BMPs, and the various software tools necessary to protect our environment. The significant improvements we're seeing in our understanding of water quality control for stormwater management come from a diverse set of sources. A major driving force is continuous research and testing of both new ideas and products, complemented by the invaluable input from expert reviewers and consultants. Regulations also play a critical role, as evidenced by the new Stormwater Rule, which became effective on June 28, 2024, with full implementation slated for December 28, 2025. This rule represents a breakthrough in how we approach and analyze stormwater issues. We're seeing more sophisticated options in areas like understanding event mean concentration, improved designs for vaults and detention ponds, and innovative solutions such as new permeable paving, advanced harvesting techniques, and systems that allow for recovery time with retention. It's crucial that any software designed to leverage these advancements receives approval from at least one regulatory agency. The security and integrity of this software and the data it handles are paramount, particularly with the rapid evolution of machine learning and artificial intelligence programming. State laws, such as FS 288.860, which addresses foreign control of intellectual property, along with guidance from the 2021 legislature and subsequent updates in December 2022, have been instrumental in safeguarding the validity and integrity of our technical information and software. Furthermore, environmental stewardship groups and municipal representatives, working in conjunction with the applicants' handbooks, contribute significantly to these ongoing improvements. We're exploring the need for more tools in our water quality management toolbox for several key reasons. First, we need to incorporate recent improvements in rules, regulations, and best practices. The goal is to develop tools that can analyze the effectiveness of our strategies more quickly and efficiently, streamlining our processes. Second, there's a critical need for consistency in how we assess environmental resource permits. Moreover, the results and insights generated by these new tools should be broadly applicable, providing valuable support for other crucial initiatives like TMDLs, BMAPs, flood control projects, and various consumptive or water use permits. Third, it's absolutely paramount that any tools we adopt or develop are based on data from Florida itself. We cannot rely on data from different climates or enforcement programs, as Florida has unique characteristics, and here effectiveness is typically evaluated on an annual basis. Finally, these tools should facilitate professional discovery and enhance our understanding of complex hydrologic events. This deeper insight will ultimately lead to improved, more effective designs for our water management solutions. The best tools are those that inspire new options and innovative ways of solving existing challenges. The State of Florida Department of Environmental Protection, or DEP, provides crucial documents like the Applicant's Handbook, Volume 1, dated June 28, 2024, to guide our work. Additionally, the 5 water management districts across Florida each have their own applicants' handbooks, which supplement and adapt this information for local conditions. These resources are vital, but there's a continuous need for improvement in how we analyze best management practices, or BMPs, and what we include in our permit submissions. Here, we'll look at some key areas identified for enhancement. First, we need to refine our understanding and use of event mean concentrations, or EMCs, including how we calculate aggregate EMCs from separate areas. This is a critical component for accurate water quality modeling. Related to specific BMPs, improvements are needed for wet detention systems, particularly addressing those without a littoral zone, as well as refining methodologies for maximum allowable pollutant loads, or MAPs, and maximum allowable retention times, ART. Accurate annual rainfall data is fundamental, and its incorporation into our analysis requires consistent updates and robust methodologies. A significant area for development involves establishing clearer and more comprehensive performance standards for BMPs. This ensures they consistently meet design objectives. We also need to consider the rapid recovery of retention volume in our designs, which impacts the system's ability to handle subsequent storm events. Another important aspect is refining the runoff reduction methodology, especially when accounting for reductions in directly connected impervious areas, or DCIAs. Understanding the media service life within filtration systems is crucial, and this analysis must consider the performance and impact of any pre-BMPs. New considerations also extend to security protection for facilities and adherence to state law concerning intellectual property related to foreign use, ensuring our systems and designs are protected. Finally, clarifying and standardizing terminology, such as distinguishing between runoff coefficient, or ROC, and the C factor, will improve consistency and communication across projects. These are all areas that have been identified as needing timely attention and completion to enhance the effectiveness and clarity of our BMP analysis and permitting processes. Continuing our discussion on potential improvements, a key area is enhancing the clarity and comprehensibility of our analysis. This includes simplifying concepts, for example, clarifying when to use fractions versus percentages, and incorporating error catches to improve accuracy. We also need to ensure the consistent inclusion of BMP names and their effectiveness ratings, aligning them with official sources like Volume 1 of the Applicant Handbook. This standardization is crucial. Further technical enhancements involve developing specific calculations for stormwater harvesting, expanding our range of available BMP designs to include newer options like advanced permeable pavements, and actively exploring new discoveries that can lead to lower cost, more effective systems. A very specific improvement is implementing effectiveness calculations for systems operating in series, directly referencing Equation 9.5 from Volume 1 of the Applicant Handbook. Additionally, we need robust pre- and post-volume calculations to support our resiliency and flood control efforts. Improvements to our cost data are essential for better decision-making, as is collecting data on how these programs impact other regulatory initiatives, such as TMDLs, BMAPs, and water use permits. Finally, a more nuanced understanding of wet detention performance is needed, particularly how it's affected by upstream retention volumes. Overall, it's vital to address all these improvements to ensure our practices and analyses remain fully consistent with current regulations and best practices. Let's consider the performance standards established by the new rule. A notable challenge is that some existing software systems haven't yet integrated these new standards, which can unfortunately lead to delays in permit acquisition. To address this, the proposed solution is to hardwire these standards directly into our processes and provide software specifically designed to implement them. These standards are informed by extensive research into water quality impacts, and we're also making an effort to maintain the formats of past worksheets to ensure continuity. This information, by the way, is detailed in A Volume 1, Section 8.3, dated June 28, 2024. Beyond the core framework, we also need to incorporate additional standards to meet various local needs or to facilitate discovery and sensitivity analysis. Specifically, there are 7 state-directed performance standards, 5 of which are dual standards, meaning they require the greater of either a specific percentage removal or a net improvement. In addition to these state mandates, local code requirements might also specify a net improvement or a particular percentage removal, such as those found in a BMAP program. We also often simply want to understand the overall effectiveness of a best management practice system. Looking at the examples, standards include ensuring that post-development impacts are less than or equal to pre-development conditions, and there are various specified percentage removals for different pollutants. For instance, you'll note the value 45, which refers to a 45% removal. This is the lowest specific removal percentage, applied to total nitrogen levels in redevelopment projects. Finally, a key component is comprehensive BMP analysis to evaluate the efficacy of these practices. This slide highlights an example of the kinds of changes introduced by the new rule, specifically referencing annual rainfall data. The information and data for analysis, including new annual rainfall figures, are often found in critical documents like the State Applicant's Handbook, Volume 1. This particular slide points to Figure 2 in Appendix M of the June 28, 2024 edition of that handbook as the official source for these updated specifications, while the slide itself humorously asks, "Where is the annual rainfall stuff?" Its purpose is to draw attention to the fact that such detailed data, crucial for many analyses, is being updated and made available through these revised official documents. We have updated annual rainfall figures, reflecting the 2024 data as specified in Appendix M, Figure 2, AH1 of the new rule. This change was implemented to meet the requirement for the most current annual rainfall information, which is now explicitly defined in the new regulations. A key benefit of this update is that an annual rainfall map is now available, enabling us to precisely determine the annual rainfall for any given location. This recent data underscores the necessity of conducting site-specific evaluations to incorporate these updated figures accurately. Here, we're examining a comparison of annual rainfall depths between 2 key periods, the year 2000 and the more recent 2024 data. The values displayed, such as 57, 55, and 61 inches, represent the frequently utilized annual rainfall data from 2000, which was published by Harper and Baker in 2007. We are contrasting these figures with the new annual rainfall depths for 2024, which are now provided by NOAA. Our analysis shows that when we compare these 2 datasets across different locations, most of the new annual rainfall totals for 2024 are greater than those from 2000. However, it's not a universal increase. Some locations show smaller rainfall amounts, and others remain roughly equal. It is absolutely critical that for any official purposes, particularly for permit applications, the most current 2024 or any other updated annual rainfall data must be used. Relying on older figures, even those as recent as 2000, may no longer accurately reflect current conditions. Event mean concentrations, or EMCs, are crucial for our modeling efforts. They represent the annual average concentration for key pollutants like total nitrogen and total phosphorus. Concentration itself is defined as the mass of a pollutant divided by its volume, typically expressed in milligrams per liter. These EMCs are then applied within our software based on the specific land use identified in a given area. Now, if a particular EMC value isn't already available in the software's pre-programmed or hardwired list, you have the flexibility to input a user-defined value. This is especially important for incorporating site-specific data that might not be captured by generic defaults. For instance, in software like BMPFast, this is done through a specific user-defined value option in a drop-down menu. This capability also extends to calculating weighted EMCs when you have a land use that's actually a combination of several different types. However, there's a trade-off with user-defined numbers. While they offer precision, they usually require a significant amount of time and effort to thoroughly justify and validate. In contrast, those pre-programmed or hardwired numbers are generally accepted without extensive questioning. When we consider wet detention pond options, particularly in the context of improving our calculations for annual load, there have been some significant advancements in how these systems are evaluated. For example, a maximum annual residence time, or ART, of 200 days is now a more commonly accepted design standard. We also give greater credit to the inclusion of a healthy littoral zone within the pond, and for the use of floating wetlands or managed aquatic plants, often referred to as MAPs. In certain permits, anoxic depth might also be a required consideration, which involves a specific calculation routine based on the input total phosphorus, or TP, value of the pond. All these factors, along with the discovery option utilizing the plot bottom feature of BMPFast, can be employed to determine how the effectiveness of these ponds changes as a function of that annual residence time. Another significant improvement we'll discuss relates to calculating retention removal, especially for sandy soils or areas where infiltration occurs at a much faster rate than typical, such as limestone regions, or through the use of select media. These are what we call fast recovery retention systems, which include exfiltration pipes, underground vaults, particularly in limestone areas, or even pumped systems where permitted. The key advantage of these fast recovery systems is a notable increase in annual effectiveness compared to slower recovery methods, specifically those with recovery times exceeding 72 hours. To determine the effectiveness, you'll first apply the removal efficiency tables outlined in the new 2024 rule, specifically in the Applicant's Handbook Volume 1, Appendix O. There are 80 such tables that cover runoff scenarios with recovery times up to 72 hours. Then, for these fast recovery systems, you adjust that initial calculation based on research, like that published by Wanyelista in 1978 and Harper in 2007, who compared the annual capture of runoff as a function of storage volume. We see that faster recovery significantly improves performance. The graph referenced indicates that for recovery times less than 3 hours, compared to 72 hours, there's an increase in effectiveness of up to 10%. An example from the Applicant's Handbook Volume 1 for Rainfall Zone 2 shows this with a treatment rate of 1 inch per day. One point of caution is that interpolating values for curve numbers and directly connected impervious areas that are not in 5-unit increments can be quite challenging. Throughout these calculations, we also assume an initial abstraction of 0.1 inch. When considering different management practices, it's crucial to account for the costs involved, particularly since some permits explicitly require these considerations. This includes both the initial construction cost and ongoing operation and maintenance, or O&M, which you can find detailed information on in the AH Volume 1, Section 12. Cost data can vary significantly depending on the specific location and circumstances. However, even with this variability, many plans necessitate an estimate of these expenses. A very valuable aspect of cost analysis is the ability to compare different scenarios. Understanding how costs change when you modify best management practices or alter land use. Tools like the BMPFast software, which draws from FSA Cunningham publications and credits Mike Harden for its calculations, allow for these important evaluations. This software helps assess construction costs, annual operating costs, the present value of an investment, and even the cost per pound of total nitrogen or total phosphorus removed. Interestingly, it also includes an option to account for potential income generated from harvesting certain resources, which can offset some of the overall costs. Here we'll delve into stormwater harvesting performance, often referred to using REV curves. Stormwater harvesting, at its core, is the process of capturing runoff water for various beneficial uses, with irrigation being one of the original and most common applications. REV curves are a critical tool used to calculate the annual capture volume, represented by E, which stands for annual capture removal or efficiency. This calculation is based on two main factors: R, which is the average daily rate of use for the harvested water, typically represented on the y-axis, and V, which signifies the volume of storage designated for harvesting. This method is officially referenced in the Applicant's Handbook, Volume 1, specifically in Appendix O, Table 1. Historically, older software used for these calculations would fix the annual runoff coefficient, or ROC, at a conservative 0.8. This value essentially assumes a highly impervious land area, leading to an estimate of removal and use that was often on the higher, more conservative side. However, newer regulations now allow for the use of a more realistic and documented ROC, providing a more accurate assessment of water use and capture effectiveness. This improved accuracy is incorporated into tools like BMPFast. Ultimately, these REV curves are developed as an average for each meteorological zone to provide consistent performance estimates. Beyond the direct scope of environmental resource permits, it's important to understand how activities within an ERP can influence other regulated programs, particularly those related to water use. A prime example of this is the harvesting of stormwater, which directly impacts water use permits. The data presented here illustrates this point by using Rain Region 2 and two different runoff coefficient, or ROC, values. A ROC of 0.8 is reflective of a highly impervious area, while 0.325 represents a mixed area with both pervious and impervious cover. As you can see, the average yearly supply of water varies significantly based on these conditions, ranging from 12.83 million gallons per year down to 7.673 million gallons per year. This substantial difference in available water supply can profoundly affect the calculations and requirements for water use permits. Once again, it's critical to note that the publication of these runoff coefficient tables within regulatory documents dictates their mandatory use in the context of environmental resource permits. Here, we're looking at REV curves, which illustrate the efficiency of harvesting. Specifically, for the discovery option, these curves show that we achieve a 61% harvested efficiency when the reliability of capture, or ROC, is 0.80. If we aim for a higher efficiency, say 90% harvested efficiency, the required ROC decreases significantly to 0.325. This demonstrates how the selection of your ROC value has a substantial effect on the overall harvesting efficiency and, consequently, on your ability to meet current regulated performance standards for stormwater harvesting. Beyond water quality, another significant social concern we must address in stormwater management is flood control. The Applicant's Handbook acknowledges this, stating that there should be at least a neutral impact in the public interest when it comes to the potential for causing or alleviating flooding problems, especially if water quality criteria are met. Flooding is, in fact, one of the most critical issues associated with stormwater runoff, and any best management practices designed for quality control must also carefully measure their impact on flood conditions. Consider this example of a land use conversion. A 16.95-acre parcel is being converted from general agricultural use to single-family residential. The site experiences an annual rainfall of 61 inches, without any stormwater management practices in place. This change in land use would dramatically increase the annual volume of runoff, jumping from an estimated 4.5 inches to a staggering 18.53 inches per year. This kind of increase would clearly exacerbate flooding problems downstream. However, with planned BMPs, we see a substantial improvement. The project aims for a net improvement in E. coli and includes features like half an inch of retention on-site using green stormwater infrastructure, followed by a detention vault. This vault will facilitate water harvesting for irrigation on 9.3 acres of land at an average rate of 1 inch per week. As a result of these BMPs, the post-condition discharge is projected to be only 3.23 inches per year, which is even less than the pre-development agricultural condition. This demonstrates that BMPs designed to hold water on site, whether for quality control or reuse, can significantly help with flood control. Furthermore, such projects must also obtain a water use permit, and meet a volume discharge limitation, ensuring that the post-development discharge volume does not exceed the pre-development volume. To truly secure a better future, we must empower the next generation of professionals with the tools and knowledge they need. This includes understanding how secure software can be incredibly helpful in responding to our societal needs. Our primary focus is to educate individuals who can actively work to protect water quality and minimize social impacts within our communities. This crucial endeavor is a lifelong commitment. You are never too young to start learning, nor too old to continue contributing. Let's talk about the name of the software we'll be discussing, BMPFast. This software is developed in C and C++ and is designed to estimate the annual removal effectiveness of various practices. Appropriately, any data saved using this software will have the extender BMPT. The acronym BMPFast itself is quite descriptive. The FAST component comes from the idea that best management practices, or BMPs, need to be analyzed within a reasonable time frame to ensure they meet both practice standards and regulatory requirements. The software's name is actually an acronym that reflects its core utility. It stands for Best Management Practices, for Annual Assessment of Stormwater Treatment. And importantly, it also carries the specific meaning of Best Management Practices with Florida-based Annual Assessment of Stormwater Treatment, which is crucial as the software is consistent with Florida's annual assessment process, particularly concerning environmental resource permits. This name truly captures the software's purpose in rapidly assessing the effectiveness of stormwater treatment. Throughout this presentation, we've explored how new rules, regulations, and evolving practices significantly impact water quality permit applications for stormwater management. We looked at specific examples to illustrate how these changes affect the permit process and how they need to be consistently applied across the state to ensure effective water quality protection. To assist with this, we introduced the software BMPFast, a valuable tool that can help streamline calculations and ensure consistency with the latest guidelines, ultimately helping you process permit applications both accurately and efficiently. Thank you for viewing and listening to this information. This module, focusing on understanding regulations, rules, and practice, is just one part of a larger series designed to help you master stormwater management for water quality control. There are at least 20 more learning modules available to further expand your knowledge in this important area. This concludes our presentation.